All right, good afternoon. Welcome to B-Sides Las Vegas Ground Truth. This talk is Attack Flow from Data Points to Data Paths by Gabriel Bassett. A few announcements before we begin. We'd like to thank our sponsors, especially our diamond sponsors, LastPass and Palo Alto Networks, and our gold sponsors, Amazon, PlexTrack, and BlueCat. It is their support, along with our other sponsors, donors, and volunteers that make this event possible. These talks are being streamed live, except of course in Underground. And as a courtesy to our speakers and audience, we ask that you make sure that your cell phones are set to silent. Questions will be at the end. If you have a question, use the audience microphone so YouTube can hear you. I am holding that mic. I will put it back on the stand in the middle of the room. As a reminder, the BSidesLV photo policy prohibits taking pictures without the explicit permission of everyone in frame. All of the talks are being recorded, again, except in Underground, and will be available on YouTube in the future. Please keep your masks on at all times. If you want to hear better, see better, feel free to move closer to the center and front of the room, keeping social distancing in mind. With that, let's get started. Please welcome Gabriel Bassett.
Yeah. Great. It's good that we get the clapping in now because you don't know what I'm going to say, and if it goes bad, at least I've gotten one clap for the presentation. So I am Gabriel Bassett. We're going to talk about attack flows. So we're going to do a quick introduction to it, and then we're going to do this like in the data-driven way, right? I'm going to show you a bunch of data, particularly data we use in information security before, like attack flow, what it looks like now. And then we're going to kind of walk through the process of taking data and turning it into attack flow. And then we're going to look at the data structured as attack flows. Then we'll wrap things up a little bit. And so, who am I? This is me. This is my Twitter handle. I have done a lot of graph things. And I want to take a second to talk about where that comes from, because I've been doing graph stuff for about 15 years now. And it started when I was in the government. When I was in the government, we were doing risk models, right? And so this is like way back. Is what we did is we came into our executive and we said, hey, we ran Nessus and we showed the output of Nessus. All of the output of Nessus. And it's a little too much. And she said, go back and find a better idea. So we came back again. And this time, we grouped things. We said, this thing happened, this high risk happened 100 times. This one happened 50 times. And she goes, that's great. I don't know what that means, right? Like, so what? So, okay, we go back to the drawing board. We come back and we got the 5x5 chart, right, that has impact, likelihood and impact on it, and it's got some red, yellow, and green areas. And we go, now we know this risk is right here, right? The problem was we never could agree because it wasn't just like one person making this decision. Like I was representing the government. I had a contractor doing the testing. Then there's the people that built the system and their government representative. And we all disagreed. And the problem was, why do we disagree? Like, why can't we all just get along? Well, it turned out that it mattered on how you made assumptions. Like, when my tester makes assumptions, they would make the assumption of like, hey, here's this server, the power button isn't like covered by a door or anything. What if someone walked in and turned that off? This is a really important server. That's a high risk. Now, understandably, the other side of the government's contractor said, yes, but that server is inside of a room that has its own access system and set of credentials that's locked down to like 20 people. And that's inside of this portion of the building that is only locked down to the people who can get access to it, which is inside of that half of the building which is locked down, which is inside of the building which has its own access, which is inside the fenced area of the base, which is inside the base. And so really, the threat over here is probably not what we're worried about. We're worried about the one out here. And see, the idea is there's a path here, right? The narrative for the threat outside the building was very different from the threat inside. And so we realized, or I realized, hey, we need to be writing that down. And so I did what everyone does when they first started to do this. They get out an Excel spreadsheet and they say, is the threat inside the building or not? If you answer, yes, it's high, or we add 10, and if it's no, we add 1. We come up with a bunch of questions like that, and then we add them up, and maybe we multiply them by some random number we came up with, because then it looks prettier. And then we say, any number between this and this, that's a high risk, and these are the lows. And that doesn't work. And I apologize if anyone in the room is actually still doing this. A lot of people do, it's not just you. But the problem is people already know what they want the risk to be. And after a few times using these kinds of tables, they know how to get it out. And so they come up with some narrative that fits their mental model for what that risk should be. I want it to be high, so I know I select this, this, and this thing to make it high. And so now not only are you not getting the narrative you needed, you're getting some false narrative. And so I said, well, let's scrap that. We'll go back to the 5 by 5, but when you put that dot on that 5 by 5 matrix, you're going to have to tell me why. You're going to have to write out a little paragraph that says, I think the threat does this, and then this thing happens, and then this, and then. And when I realized we were writing out, this is where I started to kind of get a little bit different from what we normally do today. And we realized that what we're really documenting was this attack path, right? The attacker does this to this system. They do this, and it has this effect. They do this, and it has this effect. A sequence of things. And so we started to build paths. And that was actually really cool. Because once you start building paths, you start asking this question, what does that mean in context? It's cool if you've got one. What if I have 10? What if my 10 all include the same thing? How can I combine those together? And I remember this moment really clearly. I'm kind of grappling with this idea. It's the end of the day, right? Everyone's kind of tired. It's me and this one guy there left. Like, I'm walking past this school, and he's like, hey, I know you've been working on that problem. My company had this project a couple of years ago that involved these things called graphs. I'm like, cool, what's a graph? He goes, I don't know. Like, he had no clue, but he understood enough to know that it might apply in my situation. So I go back home and I start searching for it. And it turns out it's a really great solution. And by the way, if you don't know what graphs are, we're going to talk about that later. 3 slides. And so I go back and I build Bayesian inference networks in the back of an Excel spreadsheet, which sounds like a bad place to do that until you realize that I was in the government, and they don't let you install things in the government. And they really don't let you install programming languages because then you can run whatever you want. But they do let you write Visual Basic because it comes with Microsoft Office. And so that's where I built this. And I left the government after a while. I got a patent around graphs. I wrote a bunch of blogs. I published some stuff. I've done a couple of talks. And that brings us to today. And so it's been clear for a long time that atomic InfoSec data is not cutting it, right? We need to be able to describe the paths and graphs attackers take, flows, so to speak. But we lacked a common language to do that. Attack flow is that common language. It's a schema for storing paths and graph data. And it's really cool because it's incredibly simple and it's incredibly strong. And if anyone wants to clap and tell me that I was great at doing this now, that's awesome, because on the next slide, I'm going to tell you that it was actually a team of people that did it. This was something done through MITRE's Center for Threat Informed Defense with like Raj at Attack IQ, Gage at Anomaly, Paolo at Fortinet, Mark at City, Ryu at Fujitsu, Andy, who's now at Apple, Mark at Title. And we were lucky we had many of the right people. Ryu worked on this stuff back like in his PhD years in the early 2000s. This guy is like so smart that like I just sit in awe. But he could be wandering around here and he's so mild-mannered that like, he passed by, we would never see him. But he's so smart and so awesome. I love Ryu. Andy was instrumental in writing Caldera. Mark was instrumental in writing Six, and of course, I've worked with graphs for a while, and I also maintain the Vera schema used by Verizon for the data breach investigation report. And so it was this team of people that did this. And so what's it look like? And so graphs are these mathematical things that they're actually pretty simple. They're made up of 2 things. They're made up of, see. Should I just press buttons to figure out which one's the laser, or should I actually think about it?
The line,
yeah, there we are.
There we go.
It's made up of dots. It's made up of lines for graphs. And so the idea is that the dots are nodes, the edges are the lines. Every edge has to have a node connected to its ends. You can't draw a line in a graph and have nothing on the end. But nodes themselves can have multiple or even no lines. So this is a graph. This is a graph. This is not quite a graph because there's no nodes on it. And there's a lot of different types of graphs. There's simple graphs, like, there's no direction. You don't know which one's the start or the end of the edge. There's directed, so it goes from something to. That's why we have this little arrow on this one. There's tree graphs. There's acyclic graphs. There's cyclic. There's directed acyclic graphs, or DAGs, which come up a lot in a lot of kind of different situations. There's also hypergraphs and property graphs, but we're going to talk about a very specific type of graph. We're going to be talking about linked data. And that means a couple of things. The first is that every node and edge is defined by a single string, a single URI specifically. And so every edge has a URI. In this one, it's RDF type, and I'll explain the RDF thing in a second. Every node has a URI. This is, I think, attack flow action 1, or Varus phishing. The only time you don't have those is when a node is a literal, so an actual, like a bunch of actual strings, not a URI, or a number or something like that. And so you combine those into what are called triples. Here we have a triple of attack flow action, RDF type, and Varus. And it's just 3 things, right? Like you can see a table with 3 columns, and you put edges in there, and you have your triples, and you have your graph. But you'll notice, right, that I didn't spell out attack flow. I defined attack flow over here as, the AF means this namespace. And namespaces are one of the cool things about linked data because you don't have to reinvent the wheel. If someone else has an entire definition of how to explain things, such as actions or assets, you can just use that. You don't have to come up with your own. In fact, a lot of it's predefined. Things like RDF define this is a type, action is a type, or actually that should go the other way. Phishing is a type of action, or action is a type of phishing. There's other namespaces that you'll see a lot. And I'm going to bring these up for a specific reason. So, like RDFS is used for labels. So if you want to give your node like a common name or something that sounds a lot better than, URI, blah, 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 blah. There's doubling core that adds things like, here's the description for the node. There's time for timestamps. And there's OWL, web ontology language. And it has a lot of useful things like this node is the same as this node, or this node has an object property or a data property of this thing. Or this is a named individual. Like there's phishing, the concept, and then there's the actual phishing action that happened as a named individual. And the reason I bring these up is because, if you go back and you go Google this, or if you're Googling it right now, it's going to scare the bejesus out of you. Because OWL does scary things. Because the people who invented OWL were a bunch of academics who were like, it's cool, we can do actual cool reasoning over this. We can do first order logic, we can do all these fancy things. And we come into it and go, that's cool, and when we need to know that, we can know that. What we want right now is to say that one node is the same as the other node. Like, we're using this much of this big thing, and we don't have to understand that big thing. It doesn't affect us in any way. But the nice thing is you have this namespace. If you have a data set, and I'll explain this a little bit later, but if you have a data set that includes something like the city of Sydney, you don't also have to say that Sydney is in Australia, that Australia is a continent, and that it has this location. Someone else has already built a graph that explains all that stuff. If you reference their Sydney node, then anyone that wants to know that stuff, they'll be able to find it. So now we know what graphs are, right? What about attack flow? Attack flow is 5 things: actions, assets, properties, relationships, and flow. So the action is the thing that happened. The asset is the thing that has its state change. Properties are the nodes that describe actions, assets, other properties, things like that. They're the descriptions. Relationships are just the edges between them. And the flow is the set of all this together. And so when we look at it as a graph, it looks something like this. We can see this causal path through the middle of it. And one thing you'll notice here is that it goes action, asset, action, asset. And that's very, very intentional. Because we'll get into it a little later, but in security, different people think about causality in different ways. If I'm a blue teamer, I think that I have an asset, and this action happened to it, because that's kind of what my logs look like. If I'm on the red team, I might say, I did this, which is an action. Then I did this, which is an action. And implicitly, it's the assets that are between that. I did this action. There's like true something. But to be able to capture all the ways that we think about security, it's important to have these and have them go back and forth. We'll see some visualizations that show that later. So now we're coming to kind of the fun part. What's our data look like today? This is the opportunity to look at a bunch of data but not use it. So starting with red team report, right? This is just something I downloaded off of pentestreports.com. And what do we see here? We see a lot of free-form text, right? Not a lot of structure, and really also not a lot of solid grouping. You can't say like, here's a concept, and there's grouping, but it's all over the place. So this is what our red team data looks like today. Now, attack simulation data, a little bit better. It's structured, right? It's a tree, but a lot of times in attack simulation data, you get a lot of raw code. It's hard to describe anything more than a single thing without having some clear code. In fact, this one single thing points to some code. And what we don't want is we don't want to have to describe our attack simulations as like arbitrary code, because we don't want to be like, hey, I need you to go run this attack simulation in your environment with your tools. Here's just arbitrary code. Have fun. Like, we want something a little bit better than that. Signatures, right? Again, structured, looks very similar to the attack flow. It's because it's like hierarchical data. But there's no real links. We're seeing one thing happening in an instant. You know, and that's, we want to be able to detect more. We want to be able to detect subtler things. We want to be able to detect multiple things. And then we get into intelligence data, right? And this is a subset of an eye chart, a very small subset of an eye chart. These are two records just off of Shodan, right? And there's some substantial problems with this. It's super dense. Also, you have duplicate data. So if I have like the same vulnerability down here, I'm going to get duplication of references, duplications of summaries. Like, those are going to be in every single record that references this vulnerability, right? That's going to take up a lot of space. But the biggest problem with this is that when we use these data structures, we don't know what's in them. And so this one, like, so over here, this is an HTTP test. This one, I don't think this one's actually an HTTP. It's a different test. It's like the HTTPS test. And there's nothing that says that they need to have the same information. So if I'm looking at my dictionaries for key that's like 5 layers down in every one of my records, it's not there in every one of my records. And this becomes this huge problem as you look through data if you don't know exactly what the entire structure of the data looks like. You know, and who wants to know the structure of all the data just to find the few things that they want to look for? And I say this from profoundly depressing experience. Okay, so moving on. Incident response data. Right, this is all very textual. It's all kind of these text files. By the way, big thanks to Chris Sanders and his training. He donated the text files for this. He's also helped out a lot. And so these are text files of indicators and information that were collected during this simulated IR. And the problem, right, is it's all text. Even some of this is structured. This is structured data, but it's being stored as text. And there's nothing that links 2222 to something in this file, it's right there, or over here, or even in the same file, other than like repping the raw text. You know, that's not very searchable. That's not very usable. You know, you're never going to find that in 6 months. And so, moving on to like threat intel. This is some noise donated, or some data donated by Gray Noise. This is actually pretty nicely structured. It's relatively clean. This one is, but you know, you can end up with raw data scanned. This one, they scan 2 ports. What if they scan every port, right? Then you get this thing that's like this big. Also, what if you have 40,000 of these? And you need to find every place that 23 is mentioned. Do you really want to look through 40,000 pieces of data to find every one that's got port 23 in it? And even when we aggregate things like threat intelligence, like I like to think that this looks good. I like to think that because I made it. You can all tell me that it looks good. You don't have to believe it though. It's all aggregated and it's pretty. It communicates. It's clean. It hides a lot of nuance because of that aggregation. We'll see that a little bit later. But even keep moving up the chain. Let's say that we're making decisions about our architecture, what we're going to invest in. How do we do that these days? We make it one-to-N list. At an organization I was at, the way we did it is the entire security department could propose projects. And they said, hey, we think it'll cost this much. Here's some text, maybe a paragraph explaining the benefit we expect to get from it. And we build, one-to-N lists. And at some point, the money runs out. You draw a line, and you fund this stuff, and you don't fund that stuff. Above the line, below the line. The problem is, there's no context to it. Do we know that email filter plus a phishing reporting button, do those really, we want to buy those together? Are those complementary? Are they duplicative? And what about the discussions at the executive level, right? A new exploit's being hit, right? Software X has been used in breaches, and those companies look like us, and the executives team says, well, are we at risk? And we say, we could be. We really don't know, right? We know that we run the software, but we don't know if we're at risk because we don't understand our context. And so there's a lot of problems here, right? Often our data is just blocks of text. It's hard to parse. It's hard for people to parse. It's hard for machines to parse. It's hard to get value from because the person has to be able to look at it and pull out the pieces and organize them in their mind because they're not organized in the text. And if you can't do that in real time when you're looking at it, what are the chances you're going to be able to find that later on and put it to use? We've got a lot of structured data. Most of it's structured either tabularly for logs or hierarchically, and that's better. But a lot of times it lacks links. Hierarchical data is not good at building sequential links to things. It can tell you something and then tell you things about those things, and those things you can tell things about. It doesn't say this thing is related to this thing is related to this thing. Also, it lacks that context. You either are putting too much context in because you're duplicating in every one of your records, or you have too little context because you can't go find the additional pieces of information about them because they have to be in the record. And if you do have all that context in your data and all this structure, it becomes so complex that you can't find anything. You need a search engine just to find minor things in your data. And so attack flow improves InfoSec data. And we're going to go through this as an example to see how that works. I like examples, so we're going to walk through it. So we said attack flow is like a schema, right? It's not a tool. It's not a solution. It's how you structure your data. And the schema itself lives as either a JSON schema or as a graph. We also have data. And this is a good example because anytime you have actions, assets, and order, you can create a flow. And it can be in incident response reports, red team reports, really any of that data we just looked at. But these are two good examples because if we look over here, if we look at what's happening in the IR report, it's very asset-centric. The mail logs show, proxy and host logs detect. Where a red team report starts with, we fished, right? We installed. It starts with the action happening. And so it's two different ways of looking at the exact same thing. But now we have our schema, we have our data, and I assume that everyone knows exactly how. We need something to put them together, which is nice because we actually have that tool. Michael Corinzo, I'm not great with names, put this together as part of the MITRE project. You define your action, and you define the mandatory properties for it. You define your asset and the mandatory property. And then you can add additional properties down below it. And these are all just kind of point and click in the user interface to build this out. And once you've built it, you can export your data as attack flow. So we can export it as a JSON schema. And the nice thing here is that actions are grouped together. Assets are grouped together, properties are grouped together. But I really prefer data as a graph. And so it's a graph stored in JSON, but it's a little bit different. It's just a list. That's what a little flat bracket tells us. Each thing in the list is a node. And so the ID of this node is action 1. And then for every one of the properties, the key is like the relationship, and the values are the other nodes. And so action 1 is a named individual. It's a type of phishing, and it's a type of attack flow action. We can also say the vector for it was email, or the description is the actor phished a victim. Things like that. And so if we want to know what a node is connected to, we can just go to that spot in the file. And then we take that graph, because let's be honest, none of us want to work with JSON directly. We want our machines to work with JSON. And we put it into a graph database. This is Ontotext GraphDB. This is one of the many, many tools you can use for this. There's tons of graph databases out there. I like this one because it has a nice UI. It's got a nice API, and there's a good free version of it. And it works great for this kind of data. But we said these are just triples. You can put them into a relational database or any other type. And we can see where this happened, right? We still have our causal path. We have actions that lead to assets, which lead to actions, which lead to assets. We have the properties, a couple other properties, and we have our flow node up here. But looking at it is fun. And I probably could spend a bunch of time up here just showing pretty pictures, but the reality is we want to use our data. And so we take that data, and the cool thing is it's in a database. It's not just living on its own in some file. We can now query it. And so we can say, on the left, what assets have been compromised? Or on the right, and I know this isn't readable, what actions have been taken? But we don't just stop there, right? Because we really want to know things like what assets were compromised in a certain window, or which action is taken most often. But that's just querying. This is in a language called Sparkle, which is a standard graph query language. But if you were storing this in a relational database, you'd be querying it with SQL. Or you could be querying it with Gremlin, or Cypher, or KQL, depending on what you're storing your data in. Anything. The nice thing is how flexible data is. And so you go find what you need in your data, and not just in individual pieces. You find it in all your data, because all your data is living in the same place. So going back to our challenges, right? Instead of a lot of text, we have nodes that represent a single concept. Instead of complex JSON, TaggFlow lets us represent the parts that we need. However, if there's more context we want, we simply link to it somewhere else. Someone has probably described it. We can go and bring in their knowledge as well. The relationships are clear and explicit. We know how to connect things. And we can show causality, the paths the attacks take, right? Something we weren't able to do before. And so let's go back through our data and see what it looks like now that we've turned into TaggFlow. We start with red team data, right? It looked like this before. Now it looks like this. No one in this room is going to look at this and understand what's going on. This, everyone can look on, right? The red team started with email and phone. They fished one and fished the other. It compromised a person who made the error, gave out their personal information, or installed malware on the user device. This led to credentials and installed malware. Over here, the sensor exploited a vulnerability internally on these two systems. One allowed for additional directory transversal, which compromised PHI. And the cool thing is, not only is this much more legible, this gets fed into whatever tool you are using to store this data. This data isn't looked at once and then left on the cutting room floor. It lives in your context for your organization to use. It is nice structured data. Did you get it? I got it. Okay. Looking at attack simulation data. This is a really fun area, because right now it's we can simulate basic things, and we can write a bunch of programs that do a bunch of stuff in sequence. What if we could do it dynamically, right? And so let's say that the attackers start with the domain and email. And so what you do is you match into your graph what little subgraphs or patterns match what data I have. Well, network discovery does. And so we're going to do discovery, and maybe we discover an RDP server. Over here, if we have email, well, the action that matches that, or one of our actions matching that's going to be phishing. And so that compromises a person who makes a mistake and compromises the credentials back to the attacker. And the cool thing is, after this happens and this happens, you go back through your list of potential actions you can take, and you see which other ones match into the graph. Because we have compromised credentials and a compromised RDP server, we have a match. And so we take another action. We use those stolen credentials to compromise the RDP server. You know, the same way we think as people, we can now document that and have machine. Okay, I'm sure everyone then thinks but do we really want to do this? And you're absolutely right. We probably don't want to do this. But you can do it. I'm going to get in trouble for this one. Signatures, right? Our signatures are pretty static right now. What if they could be a little more dynamic? A process creates a file. That same process runs that file. The process is a browser, and the file isn't living in a place a browser should put files. Right now, we don't have to base detections on individual events. And the reality is there's a lot of organizations that are doing it already, but a lot of it's done in raw code and things that are not communicatable. What we want is something that's communicatable. We want a rule that I can then send to someone else to say, hey, can you test this to see if it works? You know, can you test this within the system? Our intelligence, it is convoluted. We can take it now and we can look for the parts we want. Let's say that I want to know about this vulnerability right here. And so I search for that, and then I double click that, and it says, hey, here are the instances of that vulnerability that exist. And I say, great, show me the interfaces that those are found on. It's found on this interface, and that interface, and that interface, which is found through these scans on these assets. And we can click through, and we can do it. And the first couple of times, that's going to be really cool, and you're going to enjoy that. It's going to be a lot of fun. After the first couple of times, you're just going to write a query that says, hey, tell me every system that has this vulnerability on it, and it's going to dump it out for you. It's going to find that context. And you can link in context from outside your organization if you want to know the physical locations or things like that. Our incident response data, very kind of messy, useful from a human perspective, but not well useful later on. What if we take that data and we put it into Markdown? We're defining an edge right here because we have a source, a relationship, and a target. It's just in Markdown. Now we have that, we have our incident response in our graph, in our structured data. This could potentially be living with your intelligence, with your red team data. And now when we go and look, we can go find the things we want. In fact, we could bring in that structured data that we had during our incident response and bring it into the graph directly and then output from the graph back into our Markdown, allowing us to both work as kind of text as well as structured data. Oh, and this is, let's see, this on the left, this is OntoText Graph, Vegan, and Obsidian. And I'm trying to point out tools as I go because I want to really impress on you that there is so much ecosystem that already exists around this stuff. Looking at the gray noise intel, and there's a lot. I think I parsed through an hour of data in 46,000 records. Now we can go and explore that. You know, I can go search for the vulnerability I want. And I can find every threat actor using it. And I can click through those things. And then, of course, my data, right? It's pretty, but it's hiding some things. This is what it looks like on top, and this is just what a subset of it looks like when you go start looking at the paths the attackers are taking. This is not fun to look at either. This is very messy. We'll instead look at a subset of it. Well, now we're starting to see, hey, if I'm an engineer trying to figure out where I want to apply my mitigations, maybe I'm starting to understand that. I want to put things on my server layer because it looks like my aggregated attacks are mostly coming through my server layer, either as a malicious action, probably using credentials, or as an error. But this is still a little dirty. What if instead I start to look at the path even as a couple bar charts? I look at what action happened first. What actions happen in the middle, what's happening last. I'm adding additional context that I didn't have that was obfuscated when I looked at this from a point of a single bar graph. Moving on to the budgeting, right? We just kind of picked our one-to-end list. Now, what if we go and we build out the attack flows for it? And now we're saying, okay, this mitigation right here helps with this, right? Vulnerability management probably helps with all of our servers. Two-factor authentication probably helps where we authenticate. Email filtering helps where we handle emails. Now we can put this together and say, hey, what we want to do is we want to do a couple of things together as a group. Because they add together, they form kind of a single boundary. And then we want to do these two things together because they form the next boundary. And then the next thing is to form the next boundary. We can make decisions about mitigations that complement each other. And finally, that discussion, right? This kind of awkward discussion that many of us have had in some form or fashion. What if instead of saying, oh, this vulnerability is happening, we said, this attack path is happening. And when we ask, are we at risk, we say, well, we went back and we looked at that path, we pulled that path out of our data, and we've tested our phishing defenses, and we've tested our malware response, and the likelihood of malware staying on the system is this number. The malware likelihood of being phished is this. And when we add this together, even though we know that we're vulnerable to the exploit, the overall path is low. And we can say that confidently because we queried a data set that we are storing that's storing information about the structure of our organization. It's storing information about our red team results. It's storing information about what assets live and what the likelihood is from our phishing results. And so there's even more benefits we get from the ecosystem itself. All this I've done with like open free stuff. But the nice thing is like academics have been working on RDF for years and years and a decade plus now. And they built a bunch of stuff. Like that's the good news. The bad news is they built it all on Java, but you know, you can live with that. There's databases. There's graph databases. There's every other type of database. There's huge numbers of file formats. If you like your data tabular, you can do that. If you like your data in XML, I'd like to introduce you to other data types, but you can use that. There's JSON, tab delimited, human readable things, you name it, there's a format that fits how you want to use the data. And then because it can be structured, however, it can be stored, however. And there's even like API tools, there's validation tools, there's programming tools, visualization tools, editing tools, querying tools, analysis tools. All these things already exist for us because we're working in a known ecosystem. And there's huge stores of data. There aren't great structures for security data. There are great structures for every other type of data in the world. In fact, like this is this data set that, or the data structure that Google uses to build structured data into web pages. You know, and it's all machine-to-machine readable. We don't have to be in the middle of it, and that's good. Because the reality is not everyone wants to be looking at this kind of stuff. And there's more. We can define subflows. So I can say this subset of things happens often to me. Does it happen often to you? Or we can both define those and say what things are common between us. And so going back to visualization, this is an important one because the first place people want to approach this data is as a visual graph. If you want to know more about visualization, I gave a talk on it at Microsoft Blue Hat in 2019, graph visualization. And one of the things is that after a while, you don't want to look at graphs. You just want to use the data. But it's important to kind of go through an example here. This is something I pulled out of a threat report. Have a nice graph, like you read this and you're like, hey, I know more things. And if I were to ask you, okay, go put those into practice, you're going to go, well, I guess I patched this, right? I go, well, but how are you going to apply this to your system? And then, well, no, right? Like, I can't apply this graph. I can apply knowledge I gained from it. I can't apply this. But what if we go structure it as attack flow? The attacker exploits something over here, and I've left out the properties, but you can define the type of exploit on a server, which then, using data that it also sent, runs a loader, which then adds code. We can look at this from the attack team perspective. There's the other side later you can take a picture of. And here we're looking at just the actions where the server, the asset, is the relationship between them. And so this might be how a red person wants to think about it. You know, the blue side might want to think in terms of assets, with the actions being on the edges. You know, I'm thinking about what's happening to the server, the data, and the code being loaded. And then finally, we can look at it all back together. And one of the things that I want to add is if you look at it all together, you get to carry this additional information. And so you can say, not just these things are related, but here is the requirement for this exploit to work, right? And here is the state change imposed on this server. And this server being compromised is a requirement for the loader to run. And you can put this data into a structured data set where you can analyze it and use it with all your other data. You can share it with other people. You can get their data. And we can all actually put things to use. But you may not want to always look at it, right? Like, you start to get complex attacks, and they start to get busy. There's a few things that are important for visualizing this kind of data, like grouping together nodes or putting boxes. But you know what I want to do? I want to display it like this. I've got my assets. I've got my actions as lines. I can build this as an interactive visualization. I can scroll around in it. This is an easy way to show the same thing. Just because we're using graphs doesn't mean we have to look at graphs. You know, and that's important. Because as we go into the future, right, this is a schema. This is not your single pane of glass. This doesn't solve all your problems. It's a foundation to build on. And that means building. You know, it's possible to build bad things on a good foundation. Like, I don't want to give you, like, I'm excited about this. You know, you may be too. I don't want to set you up and have you feel disappointed, because there's things to be built, right? And some people don't want to build things, right? Some people just want to, like, buy the finished house, and that's okay. That's how home builders make their money, as my home builder knows. So that's okay, and not everyone's going to get it, because the Pragel paper that, you know, Google published years and years ago, they described thinking like a node. And that's not something everyone wants to do or everyone can do, and that's okay. Attack flow can meet you where you are. And so to help people with that, we're working on things like documentation. You know, we showed you, like, here's what the data looks like before and after. I'm working on getting you documentation so that you can do that process yourself. We're also looking at building training. So, you know, I said, hey, you're going to enter information into this web app. You know, I want there to be videos so you can watch someone else do it to help train you on how to do that. And then we're working on improved tooling. And that means more and quicker ways to enter data. It means easier ways to query the data. If you've ever seen Vertex.link's storm query language, I really like it. It mirrors R's dplyr verbs. It's a great query language. I'd like to see that usable for attack flow. And it also means better visualizations, easy push button stuff for whatever kind of user you are, whether you're a red team user, a blue team, or an executive. And you know, while we're talking about things, the future, we want to talk about maybe some of the more advanced things, right? Because we said action, right? There's nothing in there that says it's attacker actions. We're using it that way. But what if I describe normal behavior as actions? I can start documenting how my system normally operates. Or what about interdependencies? Haas keynote, I assume I was running PVJ and I missed it, talked about how what he calls resilience, what I would call blast radius, the effect of one system having an adverse state on other systems. That's just an action. This system changes state, that has an action of changing the state of another system. You know, this one's availability is compromised, that one is. This one's integrity is compromised, this one's integrity. We can start to build that blast radius as a structured set of data. Or even response, right? I can say, if this system is in this state, I'm going to take this response action. You know, and document that in the exact same language as we've documented everything else. And that opens up a lot of opportunities, right? The first is just structuring path data. Right now, all of our data is logs. And it's all sequential. What would be great is if we actually were given the causal paths between our log events. And I actually know some organizations that are working on them. Additionally, you know, what if we weren't companies that can provide enrichment? So I mentioned Vertex, they sell enrichment. What if you had your organization's data structure? You didn't want to really store all of the, say, the attack techniques and stuff. What if you just wanted to call into someone else's database of what all the threat actors were? So when you saw this TTP, you go just query theirs, and you link their data into your data. And it looks like a seamless graph database from your perspective, but on the back end, it's all being linked together from all the other disparate sources. And then what we need better analysis. There's opportunity to write analysis against the data, and there's opportunity to build automation. Automation of red teams, automation of defense and blue teams. And finally, for incident response, there's the ability to apply things like link prediction. So in graphs, you can use machine learning to say, hey, given the graph we see, there may be edges that we don't see. And so we can say, we've done this incident response. This is what we've seen so far. This is our attack flow. Machine learning model, are there any edges that maybe we missed? And it goes, hey, have you considered this edge, that this action was taken related to this asset? And that gives you another place to look in your response for things the attacker may have done that you didn't know about. And so attack flow really is the next step in information security data. And if you want to go get involved or go look at it, these two repos are the place to start. MITRE's repo, it has the JSON schema, the builder, and a little bit of markdown to explain it. Also, the bottom one is the graph schema, as well as the code to convert between the two. And the reality is this is probably going to leave you with more questions or many questions. And so, because this is very new, this is something that just was published in, I think, April. Reach out. I'm here to help. I want to see this. I think it is really important for the industry to move on in how we structure data. I get a lot of security data. And so the opportunity to improve how we structure data is very central to my interests. And so reach out. I can help. I'm looking to help. And I would love to open it up for questions, but I've got 10 minutes to get back to pros versus Joes to help in the game. And so thank you very much.